Hello everybody, welcome back to the Shashwat, and this lecture is in continuation of the previous lecture of the quantum series, in which we had talked about how did classical physics fail to explain the phenomena of black body radiation. And in this video we will talk about another experiment where the classical physics does not fails only but it gets embarrassed as well. The results of this experiment were so shocking that it will make you rethink about the very nature of the light itself, and we will talk about this in very details and very explained manner and very easy manner so that you could get the concepts easily. So first of all, we will talk about what did classical physics say about light, and then we will go to the experimental setup and what is photoelectric effect and all, and we will see the experimental results. Then we will compare the experimental results with the classical theory, and then we will get the whole thing that how did classical physics get embarrassed here. So watch this video till end and subscribe the channel as well if you are interested in videos like this. Okay, so have a look at what was light as per the classical theory. So according to the classical theory, light is an electromagnetic wave. So the first line looks quite reasonable. Let's come to the second line, which is energy of light depends on its intensity, not on its frequency. So this looks quite bad to you because you must have read all the things in previous classes, but we are trying to just get the concepts that what was light as per the classical theory, and then we will see the experimental results and then we will compare the things. So the result came as energy of light depends on its intensity and not on its frequency, which will lead to the fact that brighter light would have more energy because brighter light would have more intensity, and so it will have more energy, because we have seen in the second line that energy of light depends on its intensity and not on its frequency. So let's come to the photoelectric phenomena, where we have seen that intensity would decide that how much energy does the light have. It means if there will be enough intensity, irrespective of the frequency of the light, it will be able to eject electrons from a metal surface. Okay. And then the last line came as electrons will absorb energy gradually. That means it will absorb the energy slowly, not instantaneously. So there will be a time lag as well in the entire phenomena of a photoelectric effect and the ejection of electrons, emission of electrons. Okay. So this was what light was as per the classical theory, and in the next slide and in the next page we will talk about what were the experimental setup and how did the experimental observations came and how they were shocking as well. So okay, so now let's introduce the experiment which was the main thing in the entire embarrassment of classical physics. So the experiment is photoelectric effect. So what is a photoelectric effect actually? It is basically a phenomena in which electrons are emitted from a metal surface when light falls on it. I have not mentioned the specifics in the definition, which you must have read in your class 12th or class 11th, whatever it is, that which kind of light it is, of enough frequency, of whatever it is. Okay, so I have just mentioned the simple thing which was in the experiment, which was used to describe the effect. So it is basically a light falls on it and electrons are emitted from the metal surface, and the experimental setup was quite simple, in which a clean metal surface was used and a light source which had adjustable frequency as well as adjustable intensity features in it, and there was a circuit which would help to detect the emitted electrons in it. And as you can see the experimental setup depicted here, it looks quite simple, and it looks like the classical physics would easily explain this much simple thing, but the observations were really shocking, and the classical physics actually failed here. So let's come to the observations, then we will compare the things. Okay, so let's come to the experimental observations based on the experiment. So the first thing came as the observation. So we have basically three crucial observations as per the experiment, and the first crucial observation was threshold frequency. So what is this threshold frequency? For each and every metal there exists a minimum frequency, and below this frequency there will be no electrons emitted, no matter how intense light is. So there comes the first slap on the classical mechanics. There will be no emission of electrons how intense light is. So it's all about frequency, not on intensity. And the second crucial slap, the second crucial observation was instantaneous emission. As the classical theory had explained that there will be a time gap because the electrons absorb the energy gradually, not instantaneously. But the experiment told us that if the incident light frequency is greater than the threshold frequency, then electrons are emitted instantaneously. So there will be no time gap. Second slap, chatak. And the third crucial observation was energy depends on frequency, and it can be explained further as maximum kinetic energy of emitted electrons depend on the frequency of incident light and not on intensity. Intensity only causes the number of electrons. That means if you would increase the intensity, the number of electrons would increase, not the energy. So here the three consecutive slap comes to the classical physics, and here the classical physics fails. So we will now talk about how did these things were resolved by some great guy. You all know about him. So he was Albert Einstein. So let's see how did the thing was resolved in the next slide. In the previous slide, we have talked about the classical theory and what the classical theory suggested us about light and the experimental observations very well. So the experimental observations were totally shocking and different from what the classical theory gave us. So there was a need of a new idea in this picture, and Einstein came with that idea in 1905 and suggested that light does not always behave as a wave. Okay. Light does not always behave as a wave. So here the particle picture comes in the picture. Okay, and light consists of a discrete packets of energy. Light consists of discrete packets of energy, and these packets of energy are called photons. So how much energy is there in a photon? And it is given as E equals to h mu. That's the value of energy which is contained in a photon, and where h is Planck's constant and mu is the frequency of light. The value of Planck constant is somewhat 6.62 into 10 to the power minus 34 joules second. Okay. So using Einstein's idea, the experimental observations were totally explained. So we will talk about one by one. The first thing was if photon energy is greater than if photon energy is less than the work function. So what is work functions basically? We have already talked about threshold frequency. When you will multiply it with Planck's constant, we will get the work function, and it is you can say that it is the characteristic property of every metal. If you will go beyond, if you will increase the photon energy more than that, then you will get the electrons. And if the photon energy is less than that work function, there will be no electron emission, there will be no electrons emitted, whatever the intensity is. And the second thing is, if the photon energy is greater than work function, then in that case electrons will be emitted. If you have incidental light and the photon energy is greater than the work function of the metal, then electrons will be emitted, and that would be instantaneous. That means that will be emitted instantly. There will be no time gap. And third thing is, if you will increase the intensity, the number of photons will increase and not the energy per photon. That means increasing intensity will increase the number of photons only. Thus, using the Einstein's idea, that is the photons theory, all the experimental observations have been perfectly explained. And in the next slide, we will talk about the photoelectric equation, which is very important if you are in class 12, and it will help you a lot. But on this channel, there will be a proper video for chapters if it is the syllabus of class 11th or 12th physics. So it is just the continuation of the quantum series. So we'll talk about photoelectric equation right now. Okay. So let's talk about photoelectric equation. It is a very basic equation. Okay. So it is more like E equals, wait, phi naught plus K max. It's very simple now. Okay. So basically what is E? E is the energy of photon. Energy per photon, that means the energy you are giving is E. And we have already talked about E is equals h mu. And you are just in, the light is incident on a metal surface, and there will be emission of electron. And this is all about photoelectric effect. You have incident a light of energy E, which has got photon of energy E, which is equal to h mu, and mu is the frequency of the light. And we have already talked about there will be a work function associated with this metal, and we have assumed it mu phi naught, and the value of phi naught is given as h mu naught, where mu naught is the threshold frequency. And these are the characteristic property of every metal, so it varies from metal to metal. So here E equals h mu, and phi naught is h mu naught, and then comes the K max in the picture. The energy you have given is h mu by the photon, and this much amount of energy has been spent to just free the electron from the surface. Now electron will gain some energy, electron will have some kinetic energy by virtue of which it will move or escape. So this energy will be fulfilled by the remaining energy, that means h mu minus h mu naught, and that's your K max. Okay. So here is your photoelectric equation, and it's very simple, and you will study about it in detail in class 12th. Okay. So that's it. And whatever we have talked is very important if you are studying quantum mechanics. These are very, very basic things of quantum mechanics. And what we will study in the next lecture, that means lecture 3 of the quantum series, is wave nature. The wave nature will enter in the scenario. Whatever we have talked about here was all about particle nature right now, and we will see another turning point, and that would be very interesting. We'll talk about the wave nature of things. So stay tuned for lecture 3, and subscribe the channel and like the video if you have really liked it, and get strengthen your quantum mechanics. I'm still learning. I still don't get the quantum mechanics, but still I'm trying to learn these things and spread whatever I have got so far. So there will be a very long discussion. So keep learning and keep spreading the knowledge. Thank you for watching Shashwat Days.